Can you hear the difference between CD players? This may seem like an oddly specific retro audio topic, but with the CD format making a bit of a comeback lately, I've seen people both in my own comments section and elsewhere on the internet talking a lot about it. This will probably necessarily be my second to last video on CD players for a while. I know I've been doing a lot on them lately, but I'll need to post a results video soon after this one. Of course, people have talked about the sound of CD players forever, but that didn't make any sense to me as a kid. It was the 80s. This was the future.
Techniques brings you one of the most significant advances in sound since stereo. Digital audio. Compact digital discs replace records, and lasers replace needles in Techniques compact disc players to give you the one music experience conventional stereo never could. Reality.
Heck, at first we even sought out CDs with that coveted triple D SPARS code that told us the recording never touched that filthy analog realm. CD players had different features and build quality, but to me they all sounded pretty much the same because they were digital, whatever myths and legends reviewers tried to put forth to sell magazines. Of course, CD players, as opposed to CD transports, more on that later, are really only about half digital and half as analog as any other music playing machine you may own. So I thought I'd do a test, as scientific as I can make it, that you can take part in. I've got 4 home CD players here from a variety of price points and eras, and with several different types of DACs and filters inside. As a bonus, I've also got my old portable player that I just got working again, and it has a line output. I can't get it open without breaking it, so I have no idea what's inside it, but I may as well include it. So that's 5 total CD players here that are represented. I've burned a track from the YouTube audio library onto CDR as a standard audio disc, so I can play it for you all the way through. I'll be playing this track one time, switching back and forth during playback between all 5 CD players. I'll cut between them some random number of times. All you need to do is count the number of cuts, then answer my accompanying poll that's linked below. Now, it's important to know that I am not asking you to guess which player is which, or judge the quality of the recording. I just want you to count how many times you hear a cut. Don't overthink it. I'm not trying to trick you either. I'm not going to be cutting every half second or using one player all the way through. It should be an easy test if you can really hear the differences between players. The beginning and ending don't count, just count the cuts in between. You might ask about the fact that this track originally started as an MP3, and that's true, but it's been converted to standard CD Redbook audio. 16-bit, 44.1 kHz, uncompressed, like any other CD. It's also not brick-walled like most CDs from the mid-90s onwards, so it probably actually sounds better than most CDs you have. Anyway, again, that's not the test. The test is just to listen for cuts. That's it. When you're done, go take my poll that I've linked below. Just answer how many cuts you hear. It's only like a 2-minute track, so it shouldn't take you very long. I have to give David Mellor credit for this idea, which he used specifically to test whether you can hear a DAC at all versus an original unconverted digital recording. I won't give the answer away. Go take his test if you want. He got the idea from AP Mastering, a channel I don't normally watch, but I should credit him too since he gave David Mellor the idea. Though I doubt he was the first either. It's a pretty simple idea. Links to both channels are in the description below. If you want to skip to the test itself, feel free to use the chapters below. I'll also put the timecode on the screen now. For the rest of you, I'll just give you the basics about how CD players work and why you may or may not hear the differences between them. So first, let me say that my own original conception of how CDs stored data and how CD players retrieved it was definitely oversimplified. CDs do not store data as simple ones and zeros. They store data as physical pits and lands that represent strings of bits or words. The data might be digital, but it is contained on a physical medium in the imperfect world we live in. That physical media must then be read by a theoretically precise but still physical pickup that uses light, mirrors, prisms, and a photoreceptor to convert the physical pits and lands on the CD into electrical current.
And this is the tiny laser that does all the work. A small low-power semiconductor which emits invisible infrared light and plays the record from inside out. Magnified 12,000 times, this is what the surface of the compact disc looks like. You can see the thousands of tiny pits and grooves which the laser has cut into a thin plastic sheet. When it's monitored or read off by another laser in the playback machine, the lengths of the grooves and the distances between them give varying light patterns, which are then picked up by a tiny diode.
It is a much more physical or analog process from the very start than you may have thought. Certainly than I thought when I was younger, and CDs seemed futuristic and mysterious. But as a format, CD is actually closer to vinyl than it is to something like a FLAC file on your computer. This is still pretty simplified, but the electrical current from the photoreceptor in the pickup is pretty soon passed through the digital to analog converter, or DAC, to begin to make a waveform that you can hear. The original DACs and CD players were what are commonly called resistor to resistor or ladder DACs, where an escalating ladder of 16 resistors would each flip a switch for their corresponding bit whenever they received their rated voltage. Ladder DACs could be problematic because the higher bits required tolerances that were just barely even achievable with 1980s manufacturing. In fact, Philips' early players were just straight up 14-bit players, essentially because they didn't believe full 16-bit resolution was even possible in a mass-market product at the time. After passing through the DAC, the analog signal then goes through a low-pass filter that's arguably as important as the DAC itself. That filter is what actually defines the resulting analog waveform by band limiting it. Without that band limit, the player's missing a critical piece of data to define the final waveform, and you'd just hear a bunch of noise. The low-pass filter will limit the waveform to the CD spec of 20 to 20,000 Hz, ruling out all possible waveforms except the original. The CD specification is not random. It was designed with the Shannon-Nyquist theory in mind. Science.
Science?
He didn't say science. He said pie pants.
Pie pants.
The problem is that, as you've hopefully realized by now, errors can pop up at literally any point in the process. Maybe your laser isn't reading the disk well for some reason. It's out of alignment, it's getting weak over time, your disk is scratched or dirty or whatever. Maybe your ladder DAC has resistors that are drifting out of tolerance or were never actually within tolerance to begin with, especially at those higher bits. Maybe your low-pass filter wasn't designed or manufactured well, or maybe it's also just drifting out of spec and introducing artifacts and aliasing. CD players generally had error correction to hopefully compensate for a couple of these issues, but it only worked to a point, and it only worked on certain kinds of errors. As with other audio formats, technological improvements to compact disc players were mainly intended to reduce these errors in reproducing the original waveform. That's it. It wasn't to make the sound warmer or more analog. It was always just about better reproducing that original waveform. But we're still talking about the reduction of very small errors here. Even a bad early CD player gets about 90% there. And then you've got stuff like this portable RCA player, which were commonly known to include artificial EQs to boost bass and treble, whether you wanted them to or not. This is still a thing in modern Bluetooth headphones, which is where the DAC and analog circuitry now sits when playing music from your phone or other portable device. Almost all modern Bluetooth headphones, except for very high-end stuff or studio monitors like these, will boost your bass and treble without you touching a thing. Yes, even if you have the accompanying phone app set to neutral. That's to help the music cut through noisy environments. It's well-intentioned, but yeah, I have a feeling that if you do hear any truly obvious cuts in this test, they're going to be to or from this RCA player. It was just intended for a different purpose than a home player. One of the very early ways that manufacturers attempted to reduce errors in the output waveform was with digital oversampling. This actually started with the very first Philips CD players, and other manufacturers picked it up as time went on, and the concept proved its value. Oversampling in CD players is very often misunderstood, and in fact in my research I had to go back to some very early articles in some popular stereo magazines just to verify how it really worked. There is just a lot of misinformation on the internet about it. First, there is a difference between oversampling and upsampling, and these seem to be conflated constantly on the internet. Upsampling takes a digital signal and essentially stretches it to some new sampling rate using math and interpolation. For example, converting a signal from 44.1 to 48 kHz is upsampling. Oversampling is always an exact multiple of the original sampling rate, so interpolation isn't required. With oversampling, a series of zero samples are inserted into the data stream. It's a pretty dumb process, meaning it doesn't take a lot of computational power because it's not really altering the actual data. It does make the signal quieter by whatever factor of oversampling you're using, but the player can just make it louder again with the amplification. Why would you do this? Well, it's way more technical than I want to get in this video, but it has the effect of moving a particular type of noise inherent in a digital to analog conversion well above the range of human hearing. The higher the oversampling rate, the higher the frequency that noise gets pushed up. It is an early form of noise shaping, which we'll circle back to in a minute. Again, science. It is oversampling that CD players have done from the beginning with those early Philips players. But it worked so well that everyone ended up doing it. Some people say that those early 14-bit oversampling Philips players sounded pretty good, especially compared with early 16-bit non-oversampling players, where the top 2 bits were mostly just noise anyway, if you heard them at all. Today you'll see lots of people on various audiophile forums saying they hate oversampling, which really makes no sense. That's the equivalent of saying you like noise. I think what these people really mean is that they hate upsampling, which does change the actual data stream. But not many mainstream players ever did this, really only a few higher-end ones before upsampling fell out of favor, plus some external DACs. But different strokes for different folks. If you do like noise, you do you. In the late 1980s, actually not too far into the CD format's reign, much of the industry almost simultaneously developed DACs that only used a single bit, rather than 16, 18, or even 20, as had become somewhat common in higher-end players. This was an early precursor to our modern-day Delta Sigma DACs, and was intended to fix the problem of those higher bits requiring such tight tolerances. A 1-bit DAC just needs to measure the change from one sample to the next, rather than measuring each bit directly. That means it also needs a much higher sampling rate. The upside is what's known as linearity. Each bit in the original digital signal is measured and reproduced the same as every other bit, so it's easier for the DAC to reproduce the original waveform. The downside is noise. 1-bit DACs generate a lot more random noise than older ladder DACs, though they all include very aggressive oversampling by default and necessity, and therefore push that noise way up where I'm confident no one can hear it. If this sounds familiar to anyone, that's because it ended up being the basis for DSD, the encoding format used in Super Audio CD and still in many high-res digital downloads. DSD has its data already stored as 1-bit data at very high sampling rates. But it all started with regular old 16-bit PCM CDs, which were essentially converted to DSD by these early 1-bit DACs and signal processors before then being converted to analog. Stereophile magazine actually had a great explanation of how 1-bit DACs work, and this is in comparison to the earlier ladder DACs that I already explained. So for those of you who are just listening to this video, I'm just going to read this out loud. For comparison, imagine that you were assigned to fill a bucket with a known amount of water, using measuring cups varying in size from 1 ounce to 64 ounces. Even if you use care in filling the largest cup, it might contain 63.7 or 64.5 ounces instead of 64. You can't be sure that it contains exactly 64 times as much water as the smallest cup. But there is a way to obtain an exact result. Use only the 1 ounce cup and transfer its contents to the bucket 64 times. The capacity of the cup may not be exactly 1 ounce, but as long as you fill it the same way each time, the total amount transferred will be proportional to the number of refills, an exactly linear relationship. This is the idea behind 1-bit decoding. They go on to say, of course with a small cup you'll have to work fast, but in modern digital electronics that's not an obstacle. 1-bit DACs ended up being used by pretty much everybody. They were just marketed under different names. Sony called them high-density linear converter DACs. Pioneer called them pulse flow. Philips called them bitstream. JVC had my personal favorite name for theirs, pulse edge modulation differential linearity errorless. Try saying that 5 times fast. They abbreviated it PEMDD for short, with the last D standing for digital to analog, so add that onto the name if you want. Most of these names were designed to invoke either the fact that they were much faster than ladder DACs, or that each bit on the CD was treated the same as every other bit. Techniques called their entry MASH, a charmingly Japanese, somewhat mangled acronym for multi-stage noise shaping. If you know any Japanese, you can probably see where they got that. I'll bet it was even originally mush until someone realized that would be a tough sell in English-speaking markets. A big upside for the manufacturers, and probably the real reason everybody started using 1-bit DACs, is that it was cheaper to make a good CD player with one than with a 16 or 18-bit ladder DAC. Suddenly a $150 CD player, which was about the low end at the time, could perform as well as a $600 CD player, at least in terms of the DSP, filter, and DAC. The yields were a lot better, and the tolerances a lot less strict. It was essentially a cost-cutting move. In fact, very quickly, companies like Panasonic were putting the optical servo, DSP, filter, and DAC all on one chip, reducing costs even more. 1-bit DACs started being marketed in cheaper and cheaper CD players, the idea being that you could get somewhat close to high-end performance while spending less and less money. Of course, in this race to the bottom on price, build quality suffered, displays got smaller, features were removed, and CD players generally started sucking in the 90s, just like every other type of hi-fi component. Development continued on these 1-bit DACs, and today we know them as Delta Sigma DACs. They are still used in basically anything that has a DAC, although they generally use a few bits now to further help shape and reduce noise, not just one. You may see a modern 4K Blu-ray player or a receiver or whatever say it has a 24-bit 192 kHz DAC, but what that means is that it will support media with up to those specs, not that it's an actual 24-bit ladder DAC. With continued advancements and economies of scale, it's now possible to get a decent Delta Sigma DAC chip for literally just a few bucks, and they are tiny enough to fit in your wireless earbuds. The trend nowadays among CD fans, and this actually started in the 1980s, is to have a separate CD transport and choose your own DAC. A modern external DAC will almost always be a Delta Sigma type, although there are some boutique brands making ladder DACs for those who want them, usually based on FPGA designs instead of actual resistors. Recently, there's been some hype about a sub-$200 true resistor-based ladder DAC from FIO, the same company who made the Bluetooth receiver Delta Sigma DAC that I use with my vintage stereo. And it has gotten some positive reviews. But my eyes popped when I saw that the resistors it uses have only a 0.1% tolerance. That's pretty bad for this application. And the actual measurements I've seen, as opposed to subjective reviews, pretty much confirm my suspicions about it. I probably wouldn't buy one. Well-spec'd and performing ladder DACs are predictably expensive nowadays, whereas a good Delta Sigma DAC, and remember that's not just the DAC chip, but the filter, op-amps, board, case, and design labor, can be had for $100 or less. And even a cheap one will probably outperform that $200 ladder DAC. If you really want a ladder DAC, it's almost certainly a better deal to just buy a decent older working CD player than a new transport and DAC. You may want to at least consider a higher end model though, with a higher grade set of DACs, and one for each channel, to make sure you get the full 16 bits the format is capable of. And honestly, get one with oversampling. I said the CD transport thing started in the 1980s. The two players I have that were built in 1988 both have optical and coaxial digital outputs, which essentially makes them transports if you use them that way. Many people erroneously thought at the time that this would automatically give them better sound if they were able to connect their CD player to their amp or receiver using a digital cable. The manufacturers played up this misconception, because guess what else they all sold besides CD players? Yep, amps and receivers. So now they could sell you a new receiver to go with your CD player with the promise of an all-digital signal path almost to your speaker wires. In reality, this was just moving the DAC around, and there was certainly no guarantee that the analog conversion circuit in your receiver was better than what was in your CD player. I'd argue that especially in those early days, it very likely was not. But that was the start of the CD transport, which is essentially a CD player without the DAC or analog circuitry. You can still use an older CD player with a digital output this way if you like, connecting it to a modern external DAC or directly to a receiver or amp with its own DAC. Again, I generally don't see much sense in doing either of those things, because I think the internal DACs on any half-decent CD player are just fine. But that is also part of what this test is about. Still, I'd almost definitely rather have an old CD player with a new DAC than a new CD transport and DAC. That's because old CD players are just more fun, as well as generally being better built. And if you're not using the analog stage anyway, then who cares how it actually sounds? There are people today that swear by the old ladder DACs, while there are others who won't listen to anything but more modern Delta Sigma DACs, including the early 1-bit DACs. The argument in favor of ladder DACs is usually that they sound warm or analog, whereas the argument in favor of Delta Sigma DACs is that they sound linear and clear. Of course, the arguments against each is basically the flip side of the positives. Ladder DACs sound less detailed and distorted. Warmth is distortion, after all, while Delta Sigmas sound harsh and digital. I have never really subscribed to any of this, to be honest, but I am ready and willing to be proven wrong. I am a person who generally likes things the way they were originally designed, so I may be predisposed to ladder DACs for that reason, but it's really only for that reason. I think most so-called improvements to basically any already successful product are either corporations trying to cut costs or someone trying to justify their job. On the other hand, there are people who swear up and down that their tape deck sounds as good as a CD, which is objectively impossible and subjectively nearly so. So humans are really, really bad at judging sound quality, and admitting that you have a problem with this is the first step towards recovery. Now, I know there are a lot of audiophile opinions out there about the sound of lots of things, from HDMI cables to, yes, CD players. I think you can tell how I feel about a lot of that. And I know I'm not going to convince everyone of anything with this test. That's okay. But the whole point of doing this is to try to take the subjectivity out of it. I'm a data person and an objectivist. So as long as I get a good enough sample size, I'm going to believe what my poll says. Sample size is actually a scientific concept in itself, and there are calculators out there to allow you to calculate your ideal sample size. In order to have 95% confidence in the results and a 5% margin of error, I need just 385 votes. So let's aim for that. Please take my test and do your best. God knows I don't ask you for much. I should also mention the elephant in the room, the degradation of human hearing over time, including mine, but probably yours too. I know, because I've tested it, that I've lost at least the top few kilohertz off my hearing over the years. This is normal, and it happens to literally everyone, and starting at a very early age. It's not that you just instantly go clinically deaf when you hit 50. No, even as a teenager, you might only be able to hear up to 18 kilohertz or so, and you're generally going to lose a couple of kilohertz every decade until you die of old age. It happens slowly enough that you'd never realize it unless you test it, but trust me, it is happening to you right now. It's one of life's little tragedies that as we get older and can appreciate both good music and good sound more, we slowly lose our ability to hear it. So yes, it is possible that some much younger people will hear the cuts in this test better than me or my middle-aged viewers. We will see. Now obviously we can all hear major differences in sound. We can tell the difference between a yes or a no, or between a woman's voice and a man's.
Noreen, were you hitting on him?
Noreen's not here. This is Dan.
But there's clearly a limit to what we can discern. Note my word choice there. I'm not saying differences between CD players don't exist. Spoiler alert, I've seen the waveforms and they do. I'm just questioning whether you can hear them. They're pretty small differences. Do you really have the golden ears you think you do? Let's find out. The 4 home players here represent different eras and price points, with completely different internal designs. They are the JVC XLZ555, the Pioneer PDM430, the Pioneer BDP52FD, and the Technics SLPD665. There are ladder DACs, 1-bit DACs, and modern Delta Sigma DACs. The RCA RP2458 portable player I'm including as a bonus has a mystery set of components. But this was like a $60 player even back in the day, and it was from the Philips-owned RCA at a time when Philips was promoting its Bitstream DACs. I am guessing it has a 1-bit DAC and cheap op amps to go with its bass and treble boost. I'll put a list of the players with some links to information on them in the description below. A side note, some of you may be wondering why I didn't include my Pioneer PDM900. And, well, it just won't play CDRs. I tried multiple brands and types, including some very old 650 megabyte Sonys that turned out to be completely rotten. I eventually just gave up. I may do a short test on my secondary channel at some point using a store-bought CD. I just can't do that here because it's a risk to the channel of a copyright strike. Every other player here plays CDRs with no problem. I'll of course be using the analog outputs of each player and the fixed ones if a player includes both fixed and variable. The recording setup was pretty simple, just an RCA cable straight into my sound card. I did a couple tests and it turns out my sound card gave me waveforms more faithful to the original file than any external analog to digital converter I have. That conversion though does mean the waveforms are probably not exactly the same as what came out of the players. That should not affect the test since it applies to each player equally. Again, I am not asking you to judge how close the sound is to the original, just to listen for the cuts between players. I haven't made any changes to the resulting waveforms. All I've done is cut them together and made some minor manual volume adjustments to try to get them even with each other. But there's no compression or limiting or EQ or anything else going on with this track. This is how the song came out of each CD player, using its line output. The track I'm playing is called Catching Crooks by Nathan Moore. This is a pretty even track, so you should be able to hear the cuts if there are real differences. One more caveat. YouTube will obviously compress the track no matter what I do, so if you'd like, you can download a lossless FLAC file of the cut together track at the link in the description. After some reasonable amount of time, I'll post a video sharing the results, and I will show you in that video which player is playing which section of the song. I'll also give you some commentary on what I'm seeing in some of the waveforms that may or may not affect what you hear. Lastly, I can't randomize the poll answer order, so that might affect the test results a little bit. I don't think there's anything I can really do about that, unfortunately. Maybe I can account for it somehow when interpreting the results. Anyway, without further ado, here's the song. Again, don't count the beginning or end, but count the number of cuts you hear, then vote.
With hardware and software both lined up, compact discs may well rule the roost, at least until someone perfects a method of putting Beethoven's Ninth on a silicon chip. Don't laugh. I'm assured that that day, in fact, is not too far off.